is going to present our What's Up tonight, which is detecting gravity waves, the background hum of the universe. So if you're ready, Kent, take it away, if you can. There you go. All right. I think you have to unmute,
Yeah, I
Kent.
just did.
There you go.
I also can hear you much better now since I fiddled with the volume on the audio output.
Oh, good. Okay.
So I
All
think
right.
we're good to go.
All right.
Okay. You'll notice a slight change. The title that I gave for the blurb in the newsletter said gravity waves. It has nothing to do with gravity waves. Those are
Right.
fluid dynamics phenomenon.
Yep, you're absolutely correct.
In the atmosphere and in the ocean, we're dealing with gravitational waves. With a brief history, we can go all the way back to Isaac Newton and Principia. He gave us the classical laws of motion and universal gravitation and the inverse square law. But he believed gravity acted instantaneously at a distance. In other words, speed of gravity is infinite. Then along came Pierre-Simon Laplace about 20 years later, no, 120 years later. And he made the first attempt to combine the finite speed of gravity, which wasn't fully known then, with Newton's laws. And he came up with a speed of gravity at 7 million times the speed of light. Because he didn't have benefit of the Lorentz. Maxwell came up with a dynamical theory of electromagnetic field and determined that electromagnetism propagates as waves at the speed of light. And therefore, light is an electromagnetic wave. And then he was followed by Oliver Heaviside. And in The Electrician, which was a publication of electrical engineering, he produced a gravitational analog of Maxwell's equations. Then in 1905, Henri Poincaré proposed that gravity waves move at the speed of light. And not more than about 3 weeks later, Albert Einstein published his special theory of relativity. And by the time he came up with the general theory, it pretty much told it all. Poincaré was kind of taken aback, but he didn't do some of the proper things to garner credit for the notion of gravity moving at the speed of light. I bring in this concept of the dumbbell analogy. Objects that generate gravity waves have to be moving, for one thing, but they can't be axisymmetric. If the dumbbell is rotating around its axis, it's not going to generate any gravity waves. But if it's rotating around a perpendicular to the bar, then the motion of those weights will generate gravity waves. Awfully weak and undetectable, though, for their size. So the sources of gravity waves that we can perhaps measure come in several varieties. Compact binaries, white dwarfs or neutron stars, black holes, binary black holes, that is. Supernovae will, if they expand unsymmetrically, if they would expand as a perfect sphere, they wouldn't generate any gravity waves. Spinning neutron stars, which we usually see as pulsars, will, because the surface of the neutron star, however densely compacted it is not perfectly spherical most of the time. It will have bumps as high as 4 centimeters. And finally, there's the period of inflation of the universe shortly after the Big Bang. It's presumed that that would be asymmetrical and therefore could be a very large source of background gravity waves. And we hope someday maybe to discover that. Here's a little indication of the spectrum of all along the whole spectrum of frequency. We know about the CMB. We've heard a lot about that. Pulsar timing is one way to measure those spinning neutron stars. Interferometers, either terrestrial or in space. Now, we've heard recently from a lady from Sonoma State University, the dean of the Department of Physics and Astronomy. She came and spoke to us in 2018, April 24th, 2018. And she told about the LIGO interferometer. LIGO stands for Laser Interferometer Gravity Wave Observatory. It's down here. She talked about this first one in this catalog, GW150914. Those names are assigned as to gravity wave detections with the date. So in September 14th, 2015, the very first one was detected. This is the first catalog that they came up with 11 discoveries. You'll note in the middle column, it gives the mass of the two bodies in comparison with the mass of the Earth. And you'll see down I just lost my pointer. Go back. Kind of in the middle there, GW170729 has a total mass of the two bodies of almost 80 Earth masses. And it was also the furthest away over on the third column from the right. That's the distance in parsecs. It was, or excuse me, gigaparsec, a million parsecs. That was 2,840 parsecs away. These observatories that I showed you, they're whole sky observatories, so they can't pinpoint the location of the gravity waves origin unless there are at least two or more working together. And I should point out for those of you who are familiar with, you use idle cycles in your computer to process data in the search for extraterrestrial intelligence. Well, there's one for gravity waves. It's called Einstein at Home. You might want to look into it. The data that's fed to the participants is the pulsar data because they're repeating. They're constantly emitting. It may be in, on and off periods, but they don't go away. Whereas the merger of black holes or compact binaries are a one-time event. They smash together and it's over. Here's the second catalog. It's pretty hard to read, but if you look at the rightmost column of the binary black holes. There are only two in there that may be a black hole combined with a neutron star. They're a little unsure of that. This catalog shows the most massive system that, or binary that system that they found. It was almost 160 Earth masses, and the least massive that they've found so far, and this group is just 3.4. And typically, the two parties of the binary couple are mismatched in mass. It's pretty rare that they would be identical. So there's always a bigger one. So they give both the individual bodies masses. Here's the gravitational wave detectors of the past, the present, and some future plans. The first generation were called resonant mass detectors. They amounted to a solid metal bar or cylinder that would have a resonant frequency that they could use to detect the gravity waves. The second generation made them cryogenic, and the third generation was cryogenic spheres. But they ultimately found out that they were not sensitive enough. And you can see all the way up through 2003, none had ever detected a gravitational wave. So then we have the interferometers. LIGO was not most of the gravitational waves that we've been able to record so far. Second generation, they made some improvements to LIGO. LIGO consists of two systems, one on the East Coast, one on the West Coast. And in collaboration with the European group, there's a interferometer in Italy called Virgo. And Virgo often collaborates with LIGO. So they have sometimes three interferometers capturing data for a single event. And then there's some plans to go even further, the Einstein telescope, and then going out into space. Several systems there that are on the drawing board. And here's some credits to my sources, and that's all she wrote. I wonder if there are any questions. If not, I guess I'm done.
Okay. Well, thank you, Kent. That was really a good presentation. Thank you very much. Did anybody have any questions? Doesn't sound like it. Okay. Well, I think we're just going to move right on to our main event, which is, and if I get my screen sharing going here for a second.
Hey, Dave, this is Dan Vanderzanden. Can I make one quick short announcement?
Oh, sure.
Yeah, just real quick. I just wanted to remind everyone that your MDAS dues are due March 31st. And many of you have paid, so thank you to those who have, but there are quite a few who have not. And this applies to everyone, unless, of course, you've already paid. So just wanted to remind everyone. And again, the due date is March 31st. And I sent an email on February 1 with details on how to renew, or just go to the website and you can find, press the membership tab and you can renew there. So thanks.
Yeah, Dave, I'd like to slip in a brief announcement myself.
Hey, sure. Go ahead.
I could really use some What's Up presenters if anybody's willing to come forth. If you need help putting one together, I can do that too.
Okay. All right. Well, yeah, in fact, probably easiest to go ahead and contact me and I can direct it to Kent.
Yeah,
Um, Anybody who would like to.
and my email address is in the newsletter too.
Right, exactly. Yeah, and that's the other thing too, is just go ahead and contact Kent directly if you've got a subject you'd like to talk about on the next general meeting or future one, whenever. Okay, I'm going to share my screen. And if we're going to have some questions, I'm sure. So if you would please do those via chat in the Zoom, that would be great. It's hard to field questions when you're trying to present something and then people are talking. So if we go ahead and use the chat function, that'd be great. And then somebody will be watching that, including the presenter. Speaking of which is Marc Rayman, Dr. Marc Rayman, I should say properly, from NASA JPL. And he reminds us that during the pandemic, he had given a TEDx talk from his home, which is entitled, "If It Isn't Impossible, It Isn't Worth Trying." And so here's your URL for that, in case you would like to have a look at that. It's not very long and it's quite interesting. And then finally, I apologize for the color because it was white when I made it, but it went black. Anyway, so the presentation is folio, NASA's Dawn mission to the asteroid. So without further ado, I will read my little script here, which, and if I quit sharing, that would be helpful. There we go. The ambitious, exciting Dawn mission was one of NASA's most remarkable ventures into the solar system. Dawn is the only spacecraft ever to orbit a dwarf planet and the only one to ever orbit 2 extraterrestrial destinations. So Dr. Marc Rayman, who is a mission director and chief engineer, as well as a lifelong astronomy and a space enthusiast, give a fascinating and entertaining presentation on the Dawn mission and its use of ion propulsion, as well as the 2 destinations I mentioned. He will also share the excitement and profundity of controlling a spaceship in deep space. So here you go, Marc.
Thank you very much. I appreciate that introduction, and let me start sharing my screen. Can you just confirm that you can see this?
Yes, sir.
Okay, good. Well, so thanks again for the introduction, and thanks to everybody, excuse me, for showing up. As you heard, I'm going to tell you about the Dawn mission, and I work at JPL, which is run by Caltech for NASA, but there are many organizations around the country and indeed around the world involved in this project. But before I start telling you about Dawn, I want to give you some context, take you back in time a little bit, and remind you of what astronomers knew about the solar system at the beginning of the 19th century. So this is the sort of standard view of the solar system, looking down on it with the sun in the center, and you can see the orbits of the inner planets, including Earth and Mars, out to Uranus. And apart from an occasional comet and a few moons, this is pretty much what astronomers knew about the contents of the solar system. And in fact, even this was a very modern view. The same picture could not have been drawn 20 years earlier because Uranus was discovered in 1781. And so this was The other planets, of course, from Mercury to Saturn, as you know, were known even to ancient astronomers. So this was the modern view of the major contents of the solar system in 1800. Then along came these two fellows, Giuseppe Piazzi and Heinrich Wilhelm Olbers, and they got the new century off to a good start. They discovered new bodies. And because I know, and in fact was very impressed to see the sophistication of the astroimaging members of your astronomy group, I'm going to show you high resolution photographs of the two bodies that Piazzi and Olbers discovered. And they're shown here. Ceres on the left, the goddess of the Roman goddess of agriculture and grain, and Vesta, the goddess of hearth, home, and family. In fact, so Ceres is often depicted with her crown of grains and carrying her harvest bounty. And in this case, she's shown with a scythe. Different artists choose different farm implements. That's an artistic choice up to the sculptor or artist. But if you had cereal this morning, then you have at least an etymological connection with the good goddess. And Vesta on the right, the goddess of hearth, home, and family. It's interesting, relatively little is known about Vesta and how she figured into Roman mythology because she was worshipped privately in the home. And so there are fewer surviving records of her than there are for most of the gods and goddesses in Roman mythology. Now, you may have heard of the Vestal virgins, but I'm referring specifically to the goddess Vesta herself. And she's rarely depicted in art. But when she is, she often has that very stern look on her face. But one of the things I hope to convince you of this evening is that the solar system body, Vesta, is actually a much happier place. So those are the bodies that Piazzi and Olbers discovered. And now here's the same picture I showed you before. I've zoomed in to make Jupiter the outermost body, and I've added Vesta and Ceres. And you can see they fit very nicely into the gap between Mars and Jupiter. And they, along with two other bodies, for most of the next two generations, were known as planets. This was the view that in the first half of the 19th century prevailed for the understanding of the solar system. And in fact, if I don't know, so I unfortunately don't know much about the history of your astronomy group, but if any of you attended meetings of this group, say 200 years ago, then you would have differed in two interesting ways. One is you would have had even more difficulty with the Zoom connection than you're having tonight. But the other is you would have learned in school that Vesta and Ceres were planets, because that's how they were known for the first two generations of the 19th century. And in fact, I've even seen images from school books at the time that when they list the planets, after Mars, they include Vesta and Ceres before Jupiter. But as the 19th century advanced, science and technology improved, gradually the picture that astronomers had of the solar system at that time began to change as more and more and more bodies were discovered starting in the middle of the 19th century. Until now, the picture starts to look more like this. And since you, I hope my video is coming through well, and so I'll invite you to quickly verify for yourself that I've added 10,320 dots to this slide to indicate that number of asteroids today. Now, in fact, we know about many, many, many more asteroids than that. I've only shown you the ones that are larger than about 5 miles or so in diameter, Because if I showed you all of the ones we knew about, that area between Mars and Jupiter would just be a solid yellowish green mass. You wouldn't be able to see the orbits of Vesta and Ceres at all anymore. But what this shows us is that region between Mars and Jupiter is very different from the inner solar system. And in fact, if we zoom out, you can see even more clearly, excuse me, this part of the solar system is very different from the inner solar system and the outer solar system, which are largely devoid of these bodies. And of course, we call this part of the solar system the main asteroid belt. And Dawn's mission was to fly out to the main asteroid belt and study the two largest bodies there. Now, I think when most people think of asteroids, they think of, sort of chips or chunks of rock, maybe the size of buildings or mountains. That's how they're usually depicted in movies. But Vesta and Ceres really are not like that. So we can look at them in the context of other bodies in the main asteroid belt that have been studied by spacecraft. And you can see these other bodies here, as well as Vesta as imaged by Dawn, and I'll show you more pictures later. And for the lower right there, you just have to take my word for it that there are 4 asteroids in that golden box. Maybe you can see them, maybe you can't. But what this shows you is Vesta really is of an entirely different physical scale from these other bodies. And in fact, when we introduce Ceres, you can see even more clearly that they're entirely different, excuse me, from other asteroids. And in fact, there are millions, truly millions of objects in the main asteroid belt. And of that entire collection of bodies, Vesta and Ceres together have about 1/3 of the mass of that total millions of bodies. So they really are very different from most other objects in the asteroid belt. So let's take a different look, excuse me, at their size. So here they are again. Vesta, about 350 miles in diameter. Ceres, 600 miles in diameter. Once again, can compare them to the 2 largest asteroids that spacecraft had visited prior to the Dawn mission. Matilda is the largest asteroid United States spacecraft had visited. Lutetia was visited by a European spacecraft, and in both cases, the spacecraft just flew by. And in the interest of full disclosure, I should also tell you that I've exaggerated the size of Matilda here. I had to make it 1 full pixel so you could see it. And so instead of comparing them to typical, or actually those are, even Matilda and Lutetia are larger than most asteroids, we can compare them to other solar system objects that perhaps you're more familiar with. And what you can see here is Vesta and Ceres really are more like other solar system bodies. And in fact, I'm sure you remember, most people do, in 2006, when the International Astronomical Union created a new category of solar system bodies called dwarf planets. And oh my goodness, everybody thought this was awful. How could we be so inconsiderate to Pluto? Why didn't we consider poor Pluto's feelings in the matter? How could we be such an interplanetary bully? Well, whatever you think of that decision, whatever you think of it, I happen to think it was a wonderfully missed opportunity for education. But whatever you think of it, at the time that category of dwarf planets was created, Pluto was the second known body to fit in that category. Ceres, which was discovered 129 years earlier, was the first, because it satisfies all of the attributes of a dwarf planet that Pluto does. Now, when you look at a picture like this with California in it, this is deceptive because, of course, California is mostly flat. Vesta and Ceres are round, 3-dimensional bodies. So they have much more area than is suggested in an image like this. In fact, Vesta has about twice the surface area of California. So we can go into the third dimension, excuse me, and compare this map of Ceres made by Dawn with a map of the United States. And of course, I should remind you, as is the case with many astronomical images, including ones that some of you have made, the colors here don't tell you anything about the way it would look to your eye in real life. Instead, they encode some other information. But the point is, I've made the map of Ceres the correct scale compared to that of the United States. And sure, Ceres isn't as big as the United States. Ceres isn't as big as Earth, but it's still a big place. It has 37% of the area of the continental United States. And if you just think about how vast and varied and frankly beautiful the area of the United States is, it suggests there's an opportunity for a lot of diversity, a lot of different things to see on a place like Ceres. And to me, that's part of what's so exciting about sending a spacecraft there to discover what we can see. And this is some of what we saw. This is Ceres using images constructed or combined by Dawn. And in addition to many craters, you can see some linear features and other features, but most notably, you see these very bright features like this. And this is a crater that's 57 miles in diameter. And you can see in it these almost mesmerizingly bright features that just seem to cast their light out, almost like Ceres is a lighthouse shining its light out into the interplanetary seas, inviting a cosmic traveler to come in for a closer look. And that's exactly what we did. And so this is a close-up of that area that we just saw. And you can see it's really quite a mysterious, complex structure. And I'm going to show you some still closer up images soon, including especially that structure at about the 7 or 8 o'clock position there on the lower left. But I also want to show you the more diffuse area over here on the right. So I should tell you this, some of these pictures like this were taken from an altitude of just about around 240 miles, about the same altitude as the International Space Station is above the Earth. And you can see quite a bit of detail here, but I'm going to show you pictures even closer in just a moment. So first, let's change our perspective here to look at it sort of at an angle. And I want to sort of keep this perspective in mind so you can sort of track where we are as we zoom in. So we're looking to the north here, and now we're going to zoom in closer, and you still see that bright area in the center and the diffuse that was in the center, now on the left, the diffuse area off to the side. And right near the end of its mission, we took Dawn down from an altitude of about 240 miles to an altitude of only about 25 miles. So only about 3 times your altitude when you fly cross country in a jet. And it allowed us to get some remarkable views, including this one that I'm going to show you of the wall of the crater. That crater wall is a few miles high. And here you can see some extraordinary detail on it. And I just think it's really cool to be able to see this much detail on with this much structure on the wall of an alien crater. I just think that's really a beautiful picture. Now let's zoom in still more to this area here, which we saw from a higher altitude. And now you can see it at our highest resolution. Very, very strange landscape here. I mean, truly and literally alien. I mean, a square structure in the center, that in itself is pretty unusual. And these V-shaped canyons running from a little bit lower left to upper right. And let me draw your attention. I hope you can see my cursor here, but even if you can't, it's near the bottom. This sort of squiggle that suggests something flowed down a groove into this V-shaped canyon. And as we've now determined, Ceres has underground liquid water. And sometimes that water makes its way to the surface. And the water is salty, it's brine, it's salt water. When it gets to the surface, in the cold vacuum on Ceres, the water freezes and then sublimates, that is, or evaporates, goes from being a solid to a gas. The water molecules dissipate and they leave behind the salts that were dissolved in them. And so the bright structures that you see are like salt flats. But you can also see before that happened, the water actually was able to flow. And now let's flip around and view this from the other side. We're looking, zoom in a little bit. And now we're going to flip around to the other side. So instead of looking from the north, looking to the north, we're going to look to the south. And you can see this very bright structure in the center with a little mountain to the right and a dome on it. And here's the way that looked when we swooped down to really low altitude. And here again, you can see where liquid has flowed down these cracks, showing that at some time there was fluid on the surface of this alien world, fluid which we know even now persists deep underground. But again, sometimes it makes its way up to the ground. So I'm going to show you an animation, just sort of flying around a little bit of this area. Here the color, the reddish, indicates new features on the surface. These are things that are geologically young. And it just gives you a little different perspective on it. But we know, that some of this material could not persist even for hundreds of years. And so this material on the surface is being replenished quite recently, not just even in geological times, but on timescales that even we as humans can understand. So I think it's really amazing that this crater displays the liquid where there at one time, we know Ceres was covered in a global ocean of liquid water. It doesn't have that anymore, but it does still have liquid deep underground. So I actually think that's pretty remarkable. I want to now fly back up to higher altitude, show you again that crater and just how much that bright material stands out. But now I'd also like to take a different view of the limb of Ceres that you can see there, here, and you see that bump on the limb. I want to zoom in on that. There you can see it. This is the youngest volcano that we've identified on Ceres. This volcano is about 13,000 feet high, about 17 miles across at the base. And geologists have now identified more than 20 extinct volcanoes on Ceres. But I think it's really cool to recognize that, once again, this was a geologically active planet. I think a lot of people think of many solar system bodies out there as being sort of dead, inert chunks of rock. Not only did Ceres have an ocean and still has liquid underground, but it also had volcanoes, including this one, in geologically recent times. Now, on Ceres, everything is colder. It's farther from the sun. It doesn't have as strong an internal heat source anymore as it once did, nor as Earth does. And so when this volcano erupted, it didn't erupt with the kind of magma or lava that you think of here on Earth. Rather, it's what we call cryomagma, which is a mixture of mud and salt and rock and water, and it's called cryomagma. Nevertheless, the geology is very much like that of volcanoes here on Earth. I want to show you another view looking over that crater that's on the far side. So here it is. And this is a synthesized view from Dawn's actual data. And one of the things I think is cool about this is from the lowest point in that crater to the summit of this volcano is only 9 miles horizontally, but more than 24,000 feet in vertical elevation. But Ceres gravity is about a 40th of what it is here on Earth. So I think in a spacesuit, that actually could make a pretty nice hike. Only 9 miles, 24,000 feet in elevation gain. So sometime I'd like to organize a hike there. And if any of you would like to join my wife and me on that, you're welcome to join us. Here's another view that I think is really cool. This is in a different crater, which is about 1 billion years old. And I want to draw your attention to this string of small craters on the crater wall, this trail of craters. And at the end of it, note that there's a big rock. And so this rock tumbled down the crater wall. And as it bounced on the way down, it left the imprint of every place it bounced. And here's another long trail. And there's the rock at the bottom of that trail. And in fact, you can see other rocks at the end of other trails from where these things bounce down this crater wall under Ceres' gravitational pull, leaving their imprint. But part of what I think is so neat about this, with this close-up image Dawn was able to take, is, as I mentioned, this huge crater, the crater is enormous, is 1 billion years old. But these imprints are only a matter of perhaps thousands or tens of thousands of years old. Once again, reminding us that Ceres continues to be geologically active, because even in this 1 billion-year-old crater, things are still moving around. And so I think that's pretty neat. So that's just some interesting things going on Ceres. Let me take you to Dawn's other destination, Vesta. Oh no, let me first show you, forgot, there's more to come here. There are other rocks that have slid partway down the wall of this crater, but are now stuck in the ground, basically. They haven't yet succumbed to Ceres gravity, but undoubtedly sometime they will. And so I think something to look forward to is when some of these rocks have fallen the rest of the way down. So now let's turn our attention to Vesta. And here it is in the best image we had prior to the Dawn mission. This was taken by Hubble Space Telescope in the late 1990s. And again, was the best image available. And, you can't really make out a lot on this. You can see some variations in the surface, but that's about it, and the surface brightness, that is. But if you look at the shape, again, I hope you can see my cursor, but even if you can't, start in the lower left and follow the shape around and it looks pretty much planet-like. Even a little bit of flattening at the North Pole here, like many solar system bodies, including even Earth, flattened at the poles. But as you come around here, something different is going on here. You would have expected a smoother curve at the bottom here near the South Pole than what we actually see. And when astronomers got these pictures at the end of the 1990s, they concluded that what we're seeing is a giant impact crater near the South Pole with a big mountain in the center of the crater. And undoubtedly, you've seen other craters with mountains in the center. You may have seen them yourselves with your telescopes looking at the moon, or pictures of the moon or Mars. Maybe you even noticed it in some of the earlier views I showed you of Ceres, where we were looking at it rotating. Often big craters have a mountain in the center. And the reason for that is the way you make a big crater is you take a big piece of interplanetary debris, it comes screaming down into the surface and hits the ground with so much energy that the ground melts. And it actually flows away, the rock actually flows away from the impact site and then sloshes back. And as it sloshes back and cools, it solidifies. And so that peak that you see in the center of craters is like a snapshot of the process by which that crater formed. So I want to show you an artist's concept of how this giant crater may have formed on Vesta from a big piece of interplanetary debris. And so here's a piece of interplanetary debris. There's Vesta before the impact, and now here's Vesta after the impact. And you can see it excavated a huge amount of material. And some of that material went into their own independent orbits around the sun. And some of it may have made its way to the part of the solar system where you spend most of your time. And if it did, it might even have burned up in the atmosphere. And as I know you know, when you're out lucky enough to see a meteor on a nice dark night, you're seeing a piece of material from outer space burning up in the atmosphere. And you may even have seen a piece of Vesta from that impact burning up in the atmosphere. Now, when I say that, I'm not just being poetical or clever, although I am poetical and clever. I'm being serious because this is a photograph of a meteorite. I took this picture myself of a meteorite in a museum that came from that one impact at Vesta more than 1 billion years ago. And it turns out we now know that 6%, think of it, 1 in 16 of the meteorites seen to fall to Earth came from that one impact at Vesta. So these are very common, very common. And in fact, Vesta, the Moon, and Mars are the only 3 solar system bodies to which we have linked specific meteorites. But we have far, far, far more meteorites from the Moon and Mars, from Vesta than we do from the Moon or Mars. I think that's really incredible. In fact, we have more material on Earth from Vesta than we do even from the Moon, even accounting for the more than 842 pounds of material that Apollo astronauts brought back to Earth. We have tons, literally tons of material from Vesta. And so the opportunity to study this material in the laboratory and then fly a spacecraft out to Vesta to study it is particularly exciting. So once again, there's that same view of Vesta that we had from Hubble Space Telescope. And then as dawn got in, we were able to turn this into a much, much better view. And one of the first things we noticed was this triplet of craters here on the left, which we nicknamed the Snowman. And for scale, this crater is about 45 or 50 miles across. And down here, you can see this is part of the wall of this big crater near the southern, or in the south, deep in the southern hemisphere. And this is part of the mountain there. This mountain rises to more than 2.5 times the height of Mount Everest. And these crater walls are 3 times the height of Mount Everest. So your planet doesn't have topography anything like this. Now, while Dawn was at Vesta, we took more than 30,000 pictures. And unfortunately, I have to tell you that your fine astronomy club leadership didn't actually allocate me enough time this evening to show you each individual picture that we took. So instead, as at Ceres, put them together into an animation of what Vesta would look like if you were there. And so here it is. And one of the first things you'll notice is the northern hemisphere, which we're looking at here, is much more densely cratered than the southern hemisphere. Why? Because that impact deep in the south, near the South Pole, sprayed a bunch of material out, some of which escaped into space, but some of which just landed back on the ground and erased the history of craters from Vesta's first 3.5 billion years. And so the record of cratering had to start over again. Also near the top, you can see a set of grooves or troughs. These are actually Grand Canyon sized canyons that are a scar from the impact that created this crater that we're looking right into the center of now. So in the center is that mountain that's 2.5 times the height of Mount Everest. The mountain is 110 miles across at the base. And when the object that excavated this crater hit it, it imparted so much energy to Vesta that the whole body reverberated. The energy moved around inside, and hundreds of miles away, it caused the ground to be disrupted and make this set of more than or about 90 canyons near the equator that are a remnant from that impact. So quite an extraordinary event. And this picture I like because it captures so much of what's cool about Vesta. So there's that triplet of craters, the snowman, and you can see on the left the densely cratered northern hemisphere, the upper left that is, and the transition there to the more lightly cratered southern hemisphere on the right. And you can also see here a couple of the canyons here and here that are remnants from that giant impact. So I think this is neat because it just captures so much of at least those interesting aspects of Vesta. Excuse me. So that's a quick overview of Ceres and Vesta. Let me give you an idea of the overall mission. So we started from most people's favorite planet, Earth. We launched in September 2007. We used a big rocket. I threw that in just to help you stay awake late on in the evening. And on our way out to the main asteroid belt, we flew by Mars and went well beyond it, but robbed Mars of some of its orbital energy around the sun in order to help propel Vesta, in order to help propel Dawn, on its way. Now, JPL and NASA, of course, being environmentally responsible and believing in the laws of physics, we subscribe to the conservation of energy. And so for Mars to speed Dawn up, Dawn had to slow Mars down. And so Mars actually orbits the sun more slowly now than it did before Dawn flew by in February of 2009. And if you are doing the careful accounting, Mars slowed down by a velocity of 1 inch per 180 million years. So that's how much more slowly it goes now because Dawn flew by. Of course, Dawn is a little bit less massive than Mars, and so we got a little bit better velocity boost out of that. Then in July of 2011, the spacecraft got to Vesta, went into orbit around it, and spent 14 months there taking pictures and making other measurements. But then when we were finished, we actually left Vesta orbit in September of 2012, traveled for another 2.5 years to get to Ceres, and then went into orbit around it to do the same sorts of things. And at each destination, Dawn made a comprehensive set of measurements. We photographed the surface, told you we took 30,000 pictures at Vesta. We actually took 70,000 at Ceres. We took pictures at different angles so we could make stereo to determine the topography, which is how I was able to tell you the heights of some of the mountains and the depths of some of the craters. We also mapped the elemental composition. That is, what kinds of atoms are there. If you think back to maybe your high school chemistry, the periodic table of the elements, which constituents of the periodic table are present on these two bodies. And we also mapped the mineralogical composition. That is, how do these atoms come together to form molecules? In other words, what kinds of rocks are there? We also mapped the gravity field in order to measure the interior structure of these bodies. And so, for example, that let us determine that Vesta has a dense iron nickel core, just like our planet does. Now, Vesta's is no longer molten, although undoubtedly it was at some time in the past. But this once again illustrates that these bodies are not just chunks of rock. In fact, many planetary geologists now think of Vesta as more closely related to the terrestrial planets, the big rocky bodies of the inner solar system, including the one that we're on right now. Vesta is more closely related to those geologically than it is to the small chunks of rock we call asteroids. And Dawn also searched for moons because, of course, these bodies are large enough that they certainly could have moons. We didn't find any, and we don't know astronomically what that means, but there must be some information in that. And so we made these comprehensive set of measurements at these two bodies. But this picture illustrates a few interesting things to me. One is that Dawn is the only spacecraft ever to orbit a body in the main asteroid belt. It's also, as I think you heard in the introduction, it's the first spacecraft to reach a dwarf planet, Ceres, the only one to orbit a dwarf planet. But more important than any of those is that Dawn is the only spacecraft ever to orbit two separate extraterrestrial destinations, which, when you think about it, is really a pretty surprising thing. Seems like an obvious sort of thing to do that scientists would want to do. Go to one body, study it in detail, not just do a quick flyby as some missions do, but stay there for long periods of time to make comprehensive measurements, and then leave it and go elsewhere to do the same thing. So it seems like an obvious kind of mission to undertake, and it's not as if nobody ever thought of it before. Happens in science fiction all the time. You know, like places like Star Trek. Go to one body, do whatever you're going to do there, beat somebody up or make out with them, and then go to some other body and do the same thing. And yet, before Dawn, this had never even been tried. And in more than 60 years of space exploration, Dawn is the only spacecraft to do that. And so it raises the question, why is that? Why has this never even been attempted prior to Dawn? And it turns out the reason is the same reason engineers were confronted with a problem. The same problem confronted by this guy. That is, we just didn't have the technology to do what we would like to have been able to do. And the reason for that is to travel to a distant solar system body, break into orbit, maneuver in orbit as Dawn did in order to optimize its investigations, and then break out of orbit, travel elsewhere in the solar system, break into orbit again, maneuver around again. That is far, far, far beyond the capability of conventional chemical propulsion. And so in the 1990s, I got together with some colleagues at JPL, and we asked the question, how can we travel around the solar system more easily and less expensively? And our answer to that was ion propulsion. Now, excuse me, if you're like me, and I suspect many of you are, the first time you ever even heard of ion propulsion was in science fiction. And in fact, this ship here is the Star Wars TIE fighter that Darth Vader and the evil empire used to fight Luke Skywalker and other members of the Rebel Alliance. And in the Star Wars universe, the TIE fighter stands for twin ion engine, because this is the most futuristic, coolest, advanced technology George Lucas could think of. And to me, one of the rewards of working on a project like this is getting to turn the science fiction into science fact. And so here's an artist's concept of Dawn using one of its ion engines to fly into orbit around Ceres. And in fact, Dawn was able to do this because of its ion propulsion. And here's a photograph of an ion engine operating at a vacuum chamber in Pasadena, just 3 miles from where I am right now. And you can see it produces this cool blue glow like in science fiction movies. And the reason for that is we use the propellant xenon, which is like helium or neon, but heavier. And xenon just happens to glow blue like neon just happens to glow orange. And this system has 10 times the efficiency of conventional chemical propulsion. So this would be like having your car get 300 miles per gallon, which means for the same amount of propellant, we can undertake much, much more ambitious missions than we could with conventional chemical propulsion. Now, although the system is very efficient, we only flow a very small amount of xenon through the engine at a time. So it's very efficient, but the thrust is very low. It's very gentle. And in fact, I hope some of you can still see me even while you're seeing the screen here, my slide here. But if you can't, you can take my word for it that I'm holding up a single sheet of paper. And the ion engine pushes on the spacecraft as hard as this single sheet of paper pushes on my hand. But gradually in space, the effect of this gentle thrust can build up. So it turns out it would take Dawn 4 days to accelerate from 0 to 60 miles per hour. Doesn't exactly evoke the concept of a drag racer. But instead of thrusting for 4 days, if you thrust for a week or a month or a year, or as Dawn ultimately did for 6 years, you can achieve fantastically high velocity. So this is what I like to call acceleration with patience. And if you're patient, and I am, I'm a very patient guy, this is a great way to explore the solar system, because this allowed Dawn to change its velocity by far, far more than any spacecraft prior to it ever was able to do with its own propulsion system. Now, I told you the idea for ion propulsion, it's been around for a while because you saw it in a Star Wars movie, which came out in the 1977. It goes back even before that. I actually first heard of it in an episode of Star Trek from the original series, where Kirk, Spock, and Scotty admire the sophisticated capability of an alien ship that uses ion propulsion that Kirk says is beyond even their capabilities. But ion propulsion, the ideas for it go back even before Star Trek in the 1960s. Fortunately, I don't have the time tonight to give you the entire history of ion propulsion, so I will focus just instead on Dawn. And you can see the spacecraft here in an artist's concept. And the first thing you notice is these huge solar arrays. The solar arrays are 65 feet from wingtip to wingtip. When we launched this, this was the largest interplanetary spacecraft NASA had ever deployed into the solar system. And of course, the reason the solar arrays are so big is because spacecraft travels far from the sun. Sunlight is weaker, so we need a large area of solar cells to capture that faint sunlight to produce the electrical power needed to operate the spacecraft. This is our main antenna. Oh, I should also tell you, these solar arrays, wingtip to wingtip at 65 feet, that's the distance from a pitcher's mound to home plate on a professional baseball field. This main antenna here is 5 feet across. That's how we communicate with the spacecraft from across the solar system. Here's an ion engine. Here's a second ion engine. And oh boy, what do you know? We have a third ion engine here. So we actually do the Star Wars TIE fighters one better. That's an artist's concept. This is a photograph of the spacecraft when it was being built in a clean room here on Earth. And this is one of the two solar array wings. This structure on the left, here's the other. And these are folded up because, of course, you can't fit a 65-foot wide spacecraft inside the nose cone of a rocket. So these are folded up like an accordion. And when it gets into space, they open up, extend to their full reach. I like to think of it as the spacecraft opening its wings like a dragonfly as it comes out of the rocket, taking flight. Here are some of the sensors on top that we use to study Vesta and Ceres cameras and spectrometers. Other sensors. Down here in the lower right is one of the ion engines. This 1 foot diameter metal grid here has more than 15,000 little holes in it through which we shoot the xenon ions in order to get our propulsion. And the xenon is stored in a tank inside the main spacecraft structure there. And because now I've mentioned xenon a few times, I thought I'd show you a photograph of xenon. This actually is my pet chameleon xenon. And because of his color, he has sort of a cosmetic affection for xenon and ion propulsion. And I should tell you the truth, he gets a kick out of being included in my public presentations. And after this presentation, if he's not asleep tonight, it'll be fun to tell him that a bunch of sophisticated and capable astronomers and amateur astronomers 350 miles away got to see him on Zoom. So he'll think that was pretty neat. Here's another picture of the spacecraft now with one of the solar arrays deployed. And here you can see the main spacecraft structure. Here you can see some of the sensors on top. This is that 5 foot diameter antenna. This is Tom. And this is one of the two solar array wings. Each wing at 27 feet is the width of a singles tennis court. So this is really an unusually, uniquely large NASA interplanetary spacecraft. And I don't know about you, but I think interplanetary spacecraft, all spacecraft actually, are neat. I think they're neat things to look at. I don't know if you think they're neat, but I think they're neat. But one of the things that I think is even neater than what spacecraft look like is what spacecraft do. So I want to spend a moment talking about that because we use spacecraft to go far from home. This, of course, is home. And to the accuracy I can do PowerPoint, this is low Earth orbit to scale. It's space, but is not very far away. It's not very far away. In fact, the distance from you to me right now, I'm in Southern California, is greater than the distance from the surface of Earth to low Earth orbit. And this is where many spacecraft, including the International Space Station, the Space Shuttle when it was flying, and many, many other spacecraft, this is where they live. Space, but not very far away. So let's zoom out a little bit and introduce what's called geosynchronous orbit. Now in geosynchronous orbit, a spacecraft takes 24 hours to go around Earth once. That's how long the orbit takes. But of course, Earth rotates in 24 hours as well. So from the standpoint of the satellite, it's always over the same point on the ground. Or from the standpoint of the ground, the satellite is always at the same point in the sky, even as our planet rotates. And so that means that geosynchronous orbit is a very convenient location for having weather satellites, communication satellites, or other kinds of satellites that you want always to have a fixed view of the ground or to be in the same place in the sky. So for example, we don't have to keep moving our antennas around in order to stay in contact with the satellite. And at about 22,300 miles away, geosynchronous orbit is far away. That's a long distance. It's far even compared to the diameter of our planet. And in the more than 60 years of humankind sending missions into space, the overwhelming majority of spacecraft have gone to somewhere between low Earth orbit and geosynchronous orbit. So now with that context, let me move that stuff down to the corner here and introduce the moon. And now put the moon up where it belongs to that scale. The moon is really far away. The moon is 250,000 miles away. It's 10 times the distance to geosynchronous orbit. It's 30 times our planet's diameter away. The moon is really far. It's really far. And maybe you've heard rumors or tales, legends from our shared ancestry that long, long ago in the distant past, people traveled from the Earth to the moon. Most people have probably heard that. People don't do that today, right? They don't do that today. They go less than the distance from you to me, but at one time in the distant past, they did. In fact, in the late 1960s and early 1970s, 24 men traveled the distance from the Earth to the moon. And so what this tells me is this picture that we have right here shows the entire scale of firsthand, personal human experience throughout all of history. It's contained in a space illustrated by this picture. And yet, Dawn passed the orbit of the moon the day after launch. So we launched on September 27th, and on September 28th, we had the moon in our rear view mirror. So now let's introduce the next scale, which is the Earth's orbit around the sun. And of course, as the Earth goes around the sun, it brings the moon with it. So now let me put the sun here, and on the scale of the sun, this is the orbit of the moon. And on that same scale, this is the size of the Earth. The sun is so large, it's larger even than the orbit of the moon. The sun is larger than the entire range a firsthand personal human experience. The sun, is 109 times the diameter of the Earth. The sun is 864,000 miles in diameter. From this, we can conclude the sun is big. Now, with this context and scale, let me get rid of that stuff and put the sun down in the lower right corner, and to the same scale in the upper left, bring in the orbit of the Earth, magnify it momentarily just to show you that blue is the orbit of the moon. Okay, the blue dot is the orbit of the moon. The Earth is much, much too small to be seen here. And dawn was as far away as the sun in 2010. And ultimately in its mission, it was 4 times as far as the sun, more than 1,500 times as far from Earth as the moon, well in excess of 1,000,000 times farther than astronauts on the International Space Station. And honestly, I think this is amazing. On Dawn and other missions I've worked on, when the spacecraft has passed on the far side of the sun, I know this is corny, but it's true. I've gone outside and put my thumb up and blocked out the sun and thought, gosh, we have a spacecraft on the far side of the sun. This is the same sun that shone down on our planet for 4.5 billion years. This is the same sun that's the source of virtually all of the energy our planet has ever had and will ever have. This is the same sun that has so dominated human thought in art, literature, culture, philosophy, science, mythology, and religion. That's been so influential in science. And it's the same sun that's the gravitational master of our solar system, 300,000 times the mass of our planet. It's the same sun that's our signpost in the Milky Way galaxy. And yet we can send spacecraft to the far side of the sun. And when I say we, I don't mean me. I don't mean my team at JPL and NASA. I mean all of us. To me, these are Earth's robotic ambassadors to the cosmos, and they truly represent all of us, everyone. I think everyone like all of us who has ever looked up at the night sky and wonder, we all share in something like this. And that to me is really what's most remarkable about Dawn and other missions like it. I think that's really, really quite exciting and quite profound. And I hope you feel some of that too. And that raises the question then, how do we do that? How do we do this? Well, we start by putting the spacecraft on top of a huge bomb and hoping it doesn't blow up. Because as you know, these launches can really produce quite beautiful explosions. And although it's nice to have a scenic, photogenic launch, the explosions aren't the way you want to go. And this is one of the most stressful parts of a rocket scientist's career. Fortunately, Dawn got off to a very pretty launch. In fact, we launched Dawn at dawn. You can see the sun rising in the background on the left there. So we launched from Cape Canaveral in September 2007. A very pretty launch, but not the bad kind of pretty. And then once we got into space, we can follow along what our trajectory was. So here's again that conventional view of the solar system, the sun in the center. Here's the orbit of Earth. This is where Earth was when we launched. And as we follow along with Dawn's trajectory, where it's orange or sort of dark is where we were coasting, and where it's the nice xenon chameleon blue is where we were thrusting with the ion propulsion system. And so we started out coasting, and then we checked out the ion propulsion system and checked out other systems, but then got into a pattern of regularly thrusting most of the time. These regular interruptions for thrusting are just to point the main antenna to Earth for 8 hours once a week for for communications. And as a detail, the software that generated this trajectory exaggerates the duration of those short periods of communications. They actually weren't as short as suggested here. But you can see we spiral outward from the sun. We have this long coast period where we fly by Mars, slow it down, speed the spacecraft up, resume thrusting, continue our spiral outward, thrusting with the ion propulsion system. We get to Vesta, go into orbit around it, spend 14 months with it as Vesta continues its normal orbit around the sun. And we break out of orbit, travel for another 2.5 years until we get to Ceres, go into orbit around it. And then we accompanied Ceres for most of a Sirian year until the mission ended a few years ago. Now, when you see a picture like this, it's flat and it's static. And to me, it's easy to forget that everything in the solar system is in motion. In fact, I like to think of the solar system as having this big, beautiful, complex choreography, like a solar system ballet, that you can't see in a picture like this. So I want to show you an animation, but let's take a moment to orient ourselves so you can track things as the animation plays. Because if I bring in my cursor during the animation, it's gonna interfere with it. So you can see the sun in the center. The blue orbit is the orbit of Earth. The next orbit is the orbit of Mars, red for the red planet. The next orbit out to that, to the left, is Vesta, and the outermost orbit is Ceres. And we're looking at things right now the way they were in March of 2007. Remember, we launched in September of 2007. When I start the animation, this will give you a few moments to sort of synchronize yourself with the animation so you can watch as the spacecraft departs from Earth and fires up at its ion propulsion system. We'll fly by Mars, we'll aim for Vesta, we'll get there, and then eventually we'll get to Ceres. So here we go. So in September, spacecraft leaves Mars. There we are thrusting with the ion propulsion system. We won't fly by Mars till the bottom. There we go. Then we fire up the ion propulsion system. We're aiming for Vesta just to the upper left, but we still have a long way to go to get there. And Ceres, which is off the bottom right, is going to make another whole revolution around the sun before we get there. There in the summer of 2011, we got to Vesta, went in orbit around it. We're accompanying Vesta. We break out of orbit. You can see it looks like we're close to Ceres, but we're not. It's 950 million miles and 2.5 years of ion thrusting to go from Vesta to Ceres. Nevertheless, I'm gratified every time I run this animation because we always get to Ceres, go into orbit around it, and accompany Ceres in its orbit around the sun, and in fact, stay there for the completion of the mission. And so that's just a quick overview of the Dawn mission. And I'll tell you, a lot of things happen after Dawn. First of all, the spacecraft exceeded by years its expected lifetime, and it stopped operating just a couple of years ago after more than 11 years of spaceflight in a truly remarkable mission. And we left the spacecraft in orbit around Ceres, in this orbit, where every 27 hours, it goes from 2,500 miles high to plunging down to just 22 miles in altitude, and then it sails back up to 2,500 miles. But because Ceres has many of the ingredients necessary for life, I told you that we found there's water there, there's internal heat to keep the some of that water liquid. We also found organic materials and other ingredients that are necessary that we believe are important for life. We didn't discover life, but the ingredients for it, we don't want to contaminate that pristine environment with our organically dirty spacecraft. And so we intentionally left it in an orbit that would not allow it to come in contact with the ground for at least multiple decades and likely many centuries. But of course, we collected a true wealth of scientific data that will be analyzed for decades. There are a lot more things than that will happen, but I think you're probably not interested in every imaginable little thing that will come after dawn. Instead, I will just thank you very much for your attention. I appreciate you letting me tell you about the Dawn mission. And I will just conclude with something that, that Dave was kind enough to mention at the beginning, and that is if you are interested in at least some of my exploration of space and my view of the profundity of it and a life lesson that I learned. Anyway, I hope you'll take a look at my TED Talk. Only takes 16 minutes, and so maybe you'll find it worth taking a look at. But with that, I will stop sharing my screen and invite you to ask questions. And I see there's now a whole bunch of things that have been chatted. So, so let's see what some of the questions are. Oh, okay. So the first question that I can see other people have addressed other questions, which is good. But George asked, if it is so cold in Vesta, how is the water in liquid form below? So I may have misspoken. It was on Ceres that there's liquid underground. And the reason it can be liquid there, even though it's so cold, is a result of several factors. One is that the liquid has salts dissolved in it. I mentioned earlier, it's brine, it's salt water. And as you know, dissolving salt in water can lower its freezing temperature. I mean, that's why in parts of the country where there's snow and ice on the ground, they will salt the ground to melt that ice or help keep it liquid. So the materials dissolved in the water on Ceres help keep it liquid underground. In addition, Ceres, I was talking about, when I talked about how cold it is on the ground, that's on the surface. And it used to be warm enough there when it formed that there could be liquid water on the ground. There isn't anymore, but there's still internal heat left over from when Ceres formed and radioactive materials that it incorporated when it formed. As those radioactive materials decayed, they released heat. And the materials in Ceres act as a sort of an insulator. And so even over the 4.5 billion year lifetime of the solar system, that heat has not had the chance yet fully to leak out into space. And so Ceres retains some of the heat that it had even from when it formed. So, okay, Ken asked, and I will encourage you, so I should say, I wasn't actually looking at the chats during the talk. So if you said something that I should have known at the time, I didn't, but I'm seeing them now. What I was going to say is if I'm not answering your question, feel free to let me know. So Ken asked if the impact of Vesta changed its orbit. And no, it did not. The thing that hit Vesta was, the asteroid that hit it was probably 30 to 50 miles in diameter. That's pretty big. That's pretty big. But Vesta is so massive that any effect on Vesta's orbit around the sun would have been quite negligible. Just like impactors on early Earth, can make big scars, but take something really powerful to make a detectable change in the orbit. Let's see. Mike asked if there are any new ion missions on the horizon, and there are. In fact, there's one that's going to launch in August of next year. It's called Psyche, Psyche, named after the asteroid called Psyche, Psyche. It can be a little confusing to have the name of the mission have the same name as the destination, but it's building on what Dawn did. It's only going to go to one body, but it's going to a really, really cool place. Psyche, the asteroid, while obviously not as large as Vesta or Ceres, because those are the largest, it's still a very large body. What's interesting about it is it appears to be made largely of metal. And so I alluded earlier, actually didn't allude, I mentioned earlier, Vesta having a dense iron nickel core. Earth has a dense metallic core. The thinking is that one time early in the solar system's history, there may have been an early planetary type body that had a dense iron nickel core. And just like Vesta was hit by a big impactor that actually almost broke up Vesta, it didn't, but it caused quite a scar. This other body may actually have broken up, but the core may have survived. And so Psyche may be the exposed core of an early, what we call a protoplanet, an object that was in the process of growing to become a full-size planet. And so this may present a unique opportunity to look at the core, an exposed core of a planetary type body. So the Psyche mission is scheduled to launch in August of 2022. It will arrive at Psyche early in 2026 and will make the measurements there very similar to the ones Dawn made at Vesta and Ceres. And so I think that's something we can really look forward to. A couple of people applauded. Thank you very much. And seriously, I do appreciate that, but I want to answer your questions. Okay, Sean said, what would I want to learn more about in future missions that we weren't able to with Dawn? Well, so that's a good question. Actually, all these questions are good. And in fact, one of the things that NASA is studying right now is a mission to land on Ceres. So just as Perseverance landed last week on Mars, and that was the 9th mission we've landed on Mars. We're pretty good at landing missions on Mars. Landing on Ceres is much more challenging, but if you can get down to the ground, you can always get more detail. It would be wonderful to actually be able to sample that material on the surface and make even more detailed measurements of its composition. And I'm going to get to this in a moment. This mission that's being studied would do more than just land on Ceres. The idea would be to collect some of the material, that is, drill down into the ground. Excuse me. Oh, I should say, land on Ceres because the gravity is low, make some measurements, fly to another location on Ceres, perhaps make some more additional measurements there, and then try to bring the material back to Earth. Where now we wouldn't be limited by the instruments that we could put on a spacecraft, which, sophisticated as they are not nearly as capable as what you can do in a terrestrial laboratory, where, for example, you can measure the ratio of different isotopes. Maybe most of you know what isotopes are, maybe some of you don't, and given how close we are to 9 o'clock, I won't take the time to explain it now. But by measuring isotopic composition, you can more directly determine the age of the materials on the surface and learn more about how Ceres as a body formed, because we have some compelling evidence from dawn that Ceres may not have formed where it is now in the solar system. It may have formed farther out, perhaps between, or perhaps out beyond Jupiter, maybe even out beyond Saturn. And that early in the solar system's history, with the gravitational jostling among the planets, maybe you know that Uranus and Neptune likely switched position early in the history of the solar system, and Jupiter and Saturn moved around. Well, Ceres may have been caught up in that and moved from the outer solar system in, excuse me, by studying the materials that we find on the surface of Ceres and somewhat underground. We may be able to learn more about things like that as well. See, Steve asked, how do we know that there's underground brine on Ceres? Well, we know from several lines of evidence. One is that Dawn's spectrometers, instruments that we carried, were able to measure the composition of this material on the surface and see that it's salts, different kinds of salts, sodium carbonate, sodium bicarbonate, various other salts. But also with our gravity data, we, as I mentioned, we could probe underground and not only determine that these salts came from briny water underground, but even figure out that it's about 25 miles deep or so from the gravity signature. And there are other lines of geological lines of evidence from how this bright material is physically located on the ground. So the combination of composition, location, and the gravity data for underground bring all of this together to show us that that material is underground there.
Say, Mark, you can go as long as you need to.
Okay. Well, all right. So I should tell you, I have a meeting tomorrow morning at 8 a.m. So if you guys want to stick with me for the next 11 hours, you're welcome to join me.
Maybe not quite that.
Oh, okay. Okay. Well, in fact, probably around 2:30 a.m. or so, I would want to take a brief break. But anyway, thank you for allowing me to continue. But I should also say, I won't feel bad if those of you who want to get on with your lives want to depart. But let me see what the next question was here. Steve said, follow up, how is gravity measured by dawn? Okay, so here's an accurate model of Vesta right here. Let me use this as an accurate model of Vesta, my fist, and or Ceres. The spacecraft, of course, orbits around it like this, and just like satellites orbiting Earth, the spacecraft is held in orbit by the gravitational attraction from the body. But what we're measuring is not the overall gravitational attraction, but rather the variations in the gravity. And I'm going to keep explaining this. Inside Vesta, you can imagine that if it were of uniform density, then wherever dawn is in orbit, it would always be feeling the same gravitational attraction. However, suppose in my fist here of Vesta, suppose, let's see where my thumb is. Let's say it's just underground, but it's more dense. A region underground that has higher density material. Let's say it's right here, but it's underground. So as dawn is orbiting, when it gets here, it's getting closer to this higher density region. So it will be accelerated a little bit more. And after it passes over, it will be decelerated because it's pulled harder by this, and then it's pulled back and retarded a little bit in its orbit. I hope that makes sense. So the interior structure as it exerts changing pulls on Dawn based on the changing distance to Dawn, we make exquisitely accurate, fantastically accurate. I mean, this is amazing. Remember, Vesta and Ceres are out farther away than Mars, and yet we can measure the spacecraft's movement in orbit with an accuracy of less than 1 millimeter per second. That's pretty cool. That's pretty amazing, I think. And so by measuring subtle changes in the orbit, in Dawn's orbital velocity, not the kinds of things you would notice if you were looking at it. I mean, it takes, JPL's most sophisticated navigational techniques. But if you do that, then you can figure out how the mass is distributed inside to make this determination. Let's see. So Rick said, and I should say, I want to give credit to people who are also interspersing in here some very kind comments on my presentation, and I appreciate that. And you're a good audience. And I'll tell you, it's hard in Zoom, as all of you know, when you get exactly zero feedback when you're giving the presentation, because I can't see your eyes closing and you drifting off to sleep. So Rick said, how does the Dawn spacecraft slow down and assume orbit around Ceres and Vesta? Was it done only with ion propulsion? And yes, it absolutely was. We only use the ion propulsion. We could have done it with chemical propulsion to go into orbit, but ion propulsion is too efficient. So carrying extra chemical propellants to go into orbit would not have been a good use of the system. So the question for how we slow down. We're all used to the idea, we all have the concept, the mental concept of here's the planet, here's the spacecraft, it comes screaming into orbit, executes a big maneuver, and does that, right? That's how we all think of it, and that's how we've thought of it since we were in kindergarten. Scream up to the planet and drop into orbit. But with this very gentle thrust, I don't know if you were able to see my video or not earlier, but I'm pretty sure you can see me now. With the thrust of a sheet of paper, you can't break into orbit like that. However, remember when I showed you Dawn's interplanetary trajectory, and I mentioned that we were spiraling outward from the sun? If you think back on that slide, we were getting farther and farther from the sun, gently, gradually. What we were really doing was reshaping Dawn's orbit around the sun so that it got closer and closer to Vesta's orbit. I don't mean just physically closer, but we shaped Dawn's orbit so it was in the same orbit around the sun as Vesta. So we didn't have to come screaming up to it at high velocity. We were executing the same movement around the sun that Vesta was. Just like if you think of a car driving on the freeway at 70 miles an hour, and another car gets on a freeway entrance ramp and gradually gets up to speed. So here's one car moving, here's the other car matching its movement with it. Apart from air resistance, you could roll down your windows and hand something to somebody in the adjacent car, right? So we're in the same orbit. And so when Dawn got up close to Vesta, excuse me, it was going, and later Ceres, it was going in practically the same orbit. And so it just required the most gentle, gradual nudge from Dawn's ion propulsion system to go into orbit. And so in fact, when we got up to Vesta, and just before we went into orbit, we were only traveling about 50 miles an hour relative to Vesta, slower than you drive on the freeway. And so gradually with that ion propulsion system, we could just get captured into orbit. And then actually we spiraled around in Vesta orbit down to really low altitude. Then we reversed the thrust with the ion propulsion system, spiraled out away, went back into orbit around the sun, spiraled around the sun to Ceres, and did the same thing around Ceres, same thing at Ceres as we did in Vesta. Let's see, somebody, Moore said, would love to use some of the photos in your astronomy class. Are they available online? They absolutely are. You as a taxpayer already paid for this mission, and you paid for all of our pictures and all of our other data. I know you're mostly interested in the pictures, but I just want to let you know if you wanted, for some reason, our measurements of gamma ray spectra or neutron spectra or infrared spectra or gravity measurements, all that is out there. Let's see. So we took 100,000 pictures. If you are familiar with the planetary data system, which is the world's repository for all planetary images, they're there. You can, but an easier way to navigate it is, I recommend you go to a site called Photojournal, all one word, PHOTOJOURNAL, probably .jpl.nasa.gov, and search for, and it has menus you can search for different things there. You can search for pictures of Ceres or Vesta or pictures from Dawn, and you can find the pictures I showed, as well as a bunch of other cool pictures. It's a little bit easier than sorting through 100,000 pictures. We put our, sort of the favorites there, best of. They all have captions so that you can know what you're seeing. And also suggest that if you're interested in some more of the pictures with my captions for them, as opposed to sort of the official captions, I wrote a blog for the mission. It's called the Dawn Journal. And if you just search for Dawn Journal with my name, you can find that. And when we were at Vesta, we didn't yet have the capability to include in the blog pictures, but by the time we were at Ceres, we did. Do I know what the dimensions are of the underground? Oh, sorry. Renee is asking if we know the dimensions of the underground saline lakes. We do. The one on Ceres, at least the one that's under that particular crater, apparently is hundred or the scale of hundreds of miles across. There may be others that are smaller elsewhere on Ceres, and one of the things we'd like to learn more about is other pockets of briny liquid underground. But in other words, it's pretty big features there. Let's see. Bill asked, what was the time lag in transmitting commands to alter the ion propulsion? Well, and of course, there's a time lag because the speed of light is not infinite. So it takes a radio signal traveling at the universal limit to the speed of light, which, as we also know, is the speed of gravitational waves, which some scientists say shouldn't even call the speed of light anymore. Some people advocate calling it Einstein's constant because it's more than the speed of light, but it's finite. And so, I should say, Rick was kind enough to put in the chat for everyone the URL for the photojournal and the Dawn journals. So thank you, Rick. I appreciate your help with that. So back to the time lag. It depended, of course, on where the spacecraft was during its mission. I'll just tell you, when you launch an interplanetary spacecraft, the day of launch, it takes the spacecraft a while to recede from Earth. So I know I apologize. I tend to give very wordy answers. I'll get back to the specific answer. But when we start communicating with the spacecraft, it's close enough to Earth, certainly in the first few hours, that when you're in mission control, you don't even notice the time lag. You send a command to the spacecraft and you get an immediate response. A second or so delay, a couple seconds, you really don't even notice. But then a couple days later, you send the command and it takes, you know, the delay is of a time scale that we as humans start to become sensitive to. And before you know it, it's getting longer and longer and longer until over the course of the mission, at sometimes it was over an hour from the time we would send a command from the spacecraft, send a command from JPL through the Deep Space Network out to the spacecraft and get the response. So this would be like typing something on your laptop and it taking an hour until you see it on the screen. I mean, it's not for people who require instant gratification. And so, you know, you see pictures in mission control. I mean, there was this big hyped, maybe I shouldn't have put it that way, but TV event for the landing of Perseverance on Mars. But of course, the people in mission control had no more control over the spacecraft than you did, because it's too far away for real-time control. Perseverance had landed on Mars 11 minutes and 22 seconds before we saw it happen here. Dawn, again, being farther away, time delay is farther. So we don't even have people in mission control anymore, except occasionally somebody to go in, make sure that we send the commands, you know, and then you go have lunch or something or have a meeting, come back later and see what the results were. So I will infer from Bill's question, continuing with my wordiness, but he phrased it specifically about altering the ion propulsion. Of course, if you have a delay that's that long, you can't sort of joystick the ion engine to steer it exactly the way you want. And so we have to calculate exactly what the profile, sort of the flight plan, if you will be, and put it on board the spacecraft and count on it to use its smarts, to fly out that plan. So when we're in interplanetary cruise between Earth and Vesta, or between Vesta and Ceres, we update that flight profile once a month. It can't get far enough off course for it to be a problem. However, once we're in orbit around Vesta and Ceres, where the orbit period could be just a matter of hours, we can't program it for a month of thrusting and count on it to follow that accurate trajectory, because we measure the Vesta and Ceres gravity field, the way I told you, as we get closer. So when we're high up in a high orbit, we measure the gravity field as accurately as we can. But then when we tell Dawn to spiral down, it's going to get much closer. It's going to be more sensitive to the small variations in the gravity field that we can't measure from high up. So we can't plot an accurate course for it. So we give it maybe a few days worth of ion thrusting to let it get lower. Then we measure its new orbit. Then we give it a few more days of ion thrusting to let it get lower. Then we do the same thing. And so we keep updating the flight plan as it gets lower and lower and lower. I hope that answered your question, Bill. Let's see, Marnie said, I wonder when Vesta Voyages, when Vesta Voyages travel agency will start tours. I do too. And Marnie, you're welcome to sign up, but I hope I get to sign up before you do, because I'd sure like to go there. And Marnie also says, I want to see the salt flats on Ceres. And boy, I do too. I'm ready to go, but you're all welcome to join me. I look forward to that. And that was the last of the chatted questions or comments. So thanks again.
Thank you, Mark. We really appreciate it. Thank you very much.
It was my pleasure. I appreciate your all attending.
Good. I think there's lots of virtual clapping going on.
Oh, I appreciate that too. Thank you.
All right. Well, I think that pretty much wraps it up for this. And So see, I think I'm gonna have to ask Mark to stop recording because I can't, I don't think. So we could do that.